Hi, and welcome to section 7. This is the last section of the course, and here in this section we're going to present numerical nonlinear solution for the analysis of injection and fall-off test, a few analysis examples to complement the concepts, a simulation example on a case of reserves development by primary and secondary recovery, and finally the summary of the course. Let's start with the numerical nonlinear solution concept. Before we started, let's give a few comments on analytical and numerical solutions, when to use them and when not to use them. The analysis of pressure data is carried out using commercial programs, as you know, and both analytical and numerical model solutions are available. In some cases, only the numerical solution can be applied because discontinuities configuration present in the drainage area according to seismic or geological models, are not considered in the available analytical solutions. This is true for build-ups or in general, build-ups or injection or fall-off test. It is worth emphasizing that in the case of injection or fall-off test, we must consider the response of pressure to changes in relative permeabilities of both water and oil according to reservoir fluid saturation profile existent when testing the well. It is advisable to use a numerical method and include the production and injection history of all wells located in the injection pattern to determine, besides basic reservoir and well evaluation parameters, saturation profile and the current reservoir pressure, just to mention a few. This is also to make you aware that during a fall-off, you may have some interference from other wells, and you need to identify that is an interference effect. Okay, let's start giving a concept here, which is the total mobility, given by the expression is shown here, that involves the relative permeability of oil and the relative permeability of water, in the case that we're dealing with oil bank and water bank. So here it is shown the response or the tendency or signature of pressure, transient pressure during an injection period, which is, you see, is quite similar to a drawdown period. This means that here we're going to a limit, a volumetric type of limit, and over here, in this part here, is the maximum water saturation. If after finish the injection you perform or carry out a fall-off, you're going to see that the signature is the one in blue here. We have a radial flow, which is the water close to the maximum water saturation, and as we increase our investigation into the reservoir, we hit to the water bank when there is a minimum water saturation or oil saturation. Maximum, I mean. Okay, let's present a basic example using the numerical simulator, and this is the case of an injector and 3 producing wells. This injector I just intentionally fractured just to be aware that in the field cases most of the injectors are end up being fractured, and we're going to start injecting. I'll show you in the next slide the injection period and to carry out some fall-off tests. So now, using the numerical simulation, we do have to available this permeability relative permeability curve. So at any saturation or water saturation, we know what is the value of the oil permeability and the water permeability. Well, here is the history we inject during 1200 hours. This is your bottom hole pressure increasing. And finally, we decided to stop the injection and to carry out a fall-off test. The analysis of the log-log diagnostic plot for this fall-off test is shown here. You can see initially there is this tendency of linear flow due to the induced fracture, and eventually goes to stabilize over here, which is getting far from the maximum water saturation, meaning that here we're in the oil bank. Okay, here we're showing more plots applied to the fall-off. This is one very popular. This one, the idea is from this the extrapolation of this straight line is going to give you some value for the pressure, which is a P star, and should be corrected. In this case, it's going to be below the actual reservoir pressure. So there are methods to correct and get the actual reservoir pressure. Here, just to show you, this is the bottom hole well pressure increasing, and from an initial reservoir pressure of 5,000, as you see here, reservoir pressure is increasing as long as you start keep injection. And finally, over here at this point, you decided to stop injection to make a fall-off, and then your reservoir pressure is this value here. So you're supposed to get from the fall-off analysis this reservoir pressure here. Later on, I'll explain you practical issues regarding how to interpret fall-off tests. Here now we can see the saturation profile. You can, in blue, this is oil, this is let's say the bank, and because this producer is close to the injector compared to this one here, water breaks through take place about 600 hours. And finally, the reservoir pressure profile at the end of the injection period. You can see here now, this is the pressure, or reservoir pressure profile, that we're around 5,300. Okay, we started at the beginning with 5,000, as you see here. Now we were able to increase the reservoir pressure 300 psi. So we got here. Okay, now let's go and to expand our example by adding some primary production and secondary recovery. I mean, by adding a test that includes from the primary to the secondary recovery. So what we're going to see is the simulation of the expected pressure history based on the injection and production flow rates assumed in 3 injectors and 9 producing wells over a period of 308 days. And testing well initially an oil producer well in the primary stage becomes a water injection well in the secondary stage, which is normal, it happens. Just a comment, the simulation was generated using the current version of the nonlinear Sapphire program of the workstation platform from Kappa Engineering. So to do a simulation, what you have to do is just to give besides giving permeabilities and other parameters, you have to give the rates, and from the rates, this is producing rates, this is injection rates, the software is going to calculate what is the expected pressure. So what we see here, let's call this the primary production stage. It's a volumetric reservoir. We start producing. Here we have several wells producing. This is just the results in our testing well. This is a drawdown. Eventually here they decided, or we decided, to make a build-up to know the current average pressure, open the well again, and finally here the decision is to start implementing a water flooding. So we start injecting, and just for the purpose of the course, I decided to stop injection and have a fall-off in different periods of time, like a monitoring. So down here you see the values of injection rates, which is quite constant, let's say. This is one a little bit bigger. And this is, let me show you here the field. We have our well that has been under testing. The one that we're using to monitor the process is this one here. And then we have another two injectors here and producers. The way it works is I activate this producer or injectors at a time I suggest. I mean, it's not that at the initial time all of them are producing and injecting. This is the one injecting. After he produces, start injecting, and then we will see at what time this will start injection. And over here, after 307.8, this is our reservoir pressure profile. We may say that the pressure has declined from 7,000 and to around 3,000, a little bit less. And otherwise, as we shown before, it will, once we decided here, we decided to make a build-up to know the average pressure, and therefore this is the reason we start injecting here. And that's the reason the pressure has been kept at about 3,000 psi. Otherwise, it will go down if we were not, we have been not injecting water in this case. Okay, also to mention, let's go back. I like you to show you again, there is no discontinuities in the injection or drainage area of the wells. I mean, there are no faults here. This is just an homogeneous reservoir, oil reservoir. And for simplicity, you don't see any fault here or discontinuity. Okay, let's, for the first drawdown period, let's show some plots as the one here. This is the first production period before the build-up, and after this production period, we shut in the well for a build-up and trying to get the reservoir pressure. You see here that there are these deviation from radial flow, as you can see here, over here, and then eventually this one here. As I said before, there are no faults affecting the or between the wells. So you need to understand that this is due to the well interference is causing this deviation, not a discontinuity like a fault or parallel faults or similar. Same happened with the build-up. Once you shut in the build-up, you realize here that at about 0.2, 0.3 days, pressure tend to stabilize, but this is due to the producing wells interference consequence. And here I give you an idea of the isobaric or ISO values for pressure. This is not injecting yet, even though this is the error, but all these wells are producing. Before we analyze the build-up, you see they're producing 5, 6, 4 is producing, 3 is producing. This injector is not injecting during this production time. And other wells are not in production. You may say that these are infill drilling wells later on in the process. Okay, now we apply a log-log diagnostic plot to the follow-up periods, and you can see here that all are similar. There is this first radial flow, let's say, that is associated to the water bank. There is a transition, and then we're going to the oil bank, as you can see here. All of them are quite consistent in shape. The difference between pressure and derivative, as you can see here, is because of damage. The initial fall-off is 0, and then I set up some negative values for damage, and the last fall-off, although it's longer duration, it has a -4, a negative skin. And this is the isobaric after 308 days. You can see here now this is injecting and trying to support pressure over here, and therefore benefit producer 6, producer 5, 1 and 2. You can see here there is constant pressure boundaries. And the expected reservoir pressure during primary and secondary recovery stage now is the one that you see here. So this is the reservoir pressure. Then over here, pressure went down to this value here. There is no damage during production. We did this build-up just to find what is this value here. And then we start injecting here. So what you see here is the reservoir pressure, and what in practice you want to do is, once you analyze a fall-off, let's say this fall-off here, or this fall-off here, what you're looking is to find what is the average pressure of the reservoir. Of course, you can get your damage, you get many other parameters, damage, permeabilities, but analyzing this fall-off, you want to know what is the average reservoir pressure here too. So this is now again showing during the first fall-off. This is a saturation profile. You see your bank over here, and in the final fall-off, it has been, as you may guess, extended the bank. So here we're showing two plots. This is with damage equals 0, and you can see here this is your water bank. In the last fall-off, the skin is negative, so you're gonna, the tendency or the signature of the pressure is like this one here. So and then in this case over here is supposed to be the water bank. And because the fracture length probably was not long enough, and you can see this, still you can see a little bit of radial flow in the bank. And then eventually you have this transition here, similar to here. Here are some important considerations, because in many cases, even though you are trying to analyze a fall-off test and you don't want to consider other wells, well, here it gives you an idea of what is going to be the signature like. In this case, you're not considering other wells, and then this is the behavior or tendency of the pressure. If you consider all the wells, then it's quite different, the story here. You see? Similar here, this is for the case where we have a negative skin, is the last fall off, where this is going to be the tendency. And here for damage equals 0, which is the first fall off, you can see also that the tendency here is not going to be obtained if you include the other wells, which is reality. So what I'm trying to say here is that, okay, you decided not to include the other wells. Then remember that if you don't do that, maybe this behavior here, this response here is not due to transitions, or is not due to mobility changes. Is maybe that you're not including the other wells, because it should be like this. Okay, similar here during the first production period. I'm just emphasizing it because we normally, when we analyze well tests, we don't like to consider other wells. It's painful. Sometimes you decided just to do the analysis assuming that there is no interference from the other wells. It may happen that for short times you don't get that interference. I'm just telling you, in this case it's a simulated case, so we have a chance to see. So here during the first production period, if I don't consider the other wells, then you're going to have something very book case, which is your radial flow, and finally you're going to trying to go to the steady state, which is the limit. But if you include the other wells, this deviation here is not due to discontinuities, it's due to wells interference. Same thing happened to the build-up period, which you get this one here if you don't include the other wells. But if the other wells are included, you can see here is soon start getting constant the pressure because of interference, and then you have this behavior here. Okay, before going to the summary, I'd like to go back again and explain here. Let's see that what you end up in the field, what you want to do is to analyze fall-off tests. Okay, now when you decided to analyze the fall-off test, your question is, which injection history should I consider? This one here or all these to here? Okay. Okay, let's go back now to the build-up. If I analyze this build-up, I will use this production history here. I do my analysis and I end up calculating this pressure here, which was the test objective. When you enter in the software, software is going to ask you for the initial reservoir pressure, or P sub I. The initial reservoir pressure is this one here, that you enter in the software. Then eventually you have this behavior with the bottom hole pressures. Then you analyze the build-up, and you are supposed to get from the analysis, unless you do a build-up longer and longer, that you get the reservoir pressure. But as we know, we extrapolate and do some methods, and we get this point here. This is the value for your reservoir pressure. Remember here that we have other wells. This is a multi-well production. That's the reason here reservoir pressure does not stabilize, because other wells are producing. Therefore, reservoir pressure is declining. Same here in any of these build-ups, you can see that, let's say here, let's go here. You can see that here, even though you showed in the well, reservoir pressure, because of interference, is declining, because this is just one well, our monitor well. Let's see here. So let's say we want to analyze this build-up. Then there are you may say, okay, you enter the software, and then the software is gonna ask you for an initial P sub I. You're gonna say, well, I can use this one here. If you use that one, then you should include all this production here, this showed in this production, and then you go and analyze your fall-off. If you don't want to use all this history here, then your initial reservoir pressure for the software is this one. Doesn't matter if bottom hole pressure is this one here, but when he asks for the initial reservoir pressure, this is your value. So you can analyze the fall-off here. Even you can do just using this production period here, and having a value for before starting the injection, you need to have this value here, and your initial pressure is going to be this one. Then you can analyze this fall-off. Similar to, let's say, let's now go to this one, the last one. Okay, I'm going to this last one, and then I say, what should I do? Should I consider the whole thing here? You can do that, but to make it simple, you want to analyze this fall-off, you may use only this injection period here at this product injection rate, and you need to have a point here before a pressure point here before starting the injection period, or the reservoir pressure at that moment. Then when you analyze the fall-off, you need to simulate back to this point here. But no, this is, I'm telling you, because the software is going to ask you for that pressure. So this is, let's say, a tip. I saw in many cases that nobody cares about giving this value, and they're playing until they get a good match for the fall-off. And the fall-off is getting a good match, but not necessarily the correct one. Okay, let's go to draw a summary of the course. And as I said, if you have any doubts, you can reach me or send me a message, and I'll be glad to help you if there are some doubts regarding all the material in the course. Okay, so according to the literature review, the analytical solution given by the two-bank or multi-composite reservoir model should be considered as a starting point for data interpretation for either water or polymer injector wells. Fall-off tests are the ones commonly carried out in practice. Although both analytical and numerical approach can be used for data analysis, the numerical nonlinear approach is suggested. If you don't want to enter this, remember, then when you analyze the shape, the signature of the fall-off, then keep in mind that there are some issues related to effects by interference of other wells. Data acquisition. Acquiring pressure data is critical, and in the ideal case is not to stop injecting to start the pressure gauge. In practice, this sometimes is not gonna be done. In order to define the value of the injection closing time, like in the build-up, you need the T sub 0 before analyzing the build-up. You need the pressure, drawdown pressure just before starting the first build-up pressure. Here, you need the injection, the last value of the injection pressure to analyze the fall-off. In the case of polymer injector wells, acquiring fall-off pressure data should be done using a downhole pressure gauge and shut-in valve to minimize wellbore storage effect. in order to identify polymer zone needed to calculate polymer and all region parameters, distance to polymer front, polymer viscosity, mobility ratio, just to mention a few. And from a practical point of view, a fracture is going to be induced in the injector well. Depending on its length, the fracture presence could make difficult to identify the radial flow regime. Maybe it's not existent because the fracture dominates and then you go to the oil bank. So you don't see any radial flow regime in the water bank. And in the case of well completion with permanent downhole pressure gauges, all algorithms, artificial intelligence algorithms, as well as machine learning approach for data analysis has been underway with quite a good success during the past 10 years, according to published papers on the subject. Well, this is the end of the course, and I really thank you for training with us. And any questions, again, you may reach me via email or WhatsApp or any other means, and I'll be glad to help you if there are any questions related to the course. Thank you again for your attendance.